Hi, and welcome back to Algebra 1. Our goal for today is to continue working with our simplifying when we have radicals involved. At this point with our square root problems, we should be able to evaluate a problem that has a radical sign in it where the number underneath is a perfect square that results in an integer or just a counting number result. So for example, if I have the radical sign there to begin with, I'll have one positive integer and an answer when I have one number underneath that is a perfect square. Or I might end up with a problem where I have to evaluate using PEMDAS where I end up with one number underneath that's a perfect square. And since the radical sign was there to begin with, in my problem, I'll have one positive number or one positive integer when I evaluate the square root, and then keep going and finish PEMDAS from there. If I don't have a radical or square root sign to begin with, and I'm asked for possible roots, then I have to think about the possibility that I could take a positive number and square it and end up with that number, but I could also take a negative number and square it and end up with that number. And in that case, we have two possible roots or two possible square roots that I have to count for. A positive integer and the negative integer. They're going to be opposites of each other, but I have to count for both, not just the positive ones, so be careful. I promise people are going to leave off the negative option for this one, so be careful. So yesterday we started to look at, well, what if my number underneath the radical sign is not a perfect square? And if I were to type it into my calculator, I would end up with the irrational decimal version, the non-terminating, non-repeating version of that number. And in that case, we don't want to give an approximate decimal number. We want to give the exact simplified version. So for today, you should not be typing in second x squared to get your square root, enter. If it doesn't give you back a perfect square, you shouldn't be stopping there. I do not want decimal answers. So please do not give me decimal answers because our goal for today is to write it in its most basic simplified version, not give an approximate decimal version. So reminders from previous learning is that our goal then is to use prime factorization to break down the value that's underneath the radical sign. Once we use our prime factorization to break down our number underneath the radical sign, we're looking for things that are perfect squares. The way that we find those perfect squares is we find two of the same factor. Wherever we have two of the same factor, that would represent a number that would be a perfect square that can get simplified out from underneath the radical. Anything that is not part of a perfect square has to remain unsimplified where it started, which is it started underneath the square root sign. For whatever reason, people will take the two things and flip-flop. They'll leave the perfect squares underneath and put the ones that should have stayed underneath, the leftover ones on the outside. Remember, to be simplified, it has to be part of a perfect square. All right, if it's not part of a perfect square, it can't go anywhere, it can't move, it's got to stay put. So, picking up where we left off with our example number 5 yesterday. This was our last one we did in our previous learning. So example number 6 in our notes. I want to simplify here when we have a 5 times the square root of 200, n to the second, r to the fifth. Please remember that this n has no exponent on it, so technically that's an n to the first. This 2 only goes to this n, so be careful when you break down your factors in your tree. I remember this is a 5 that's right next to a grouping symbol, in this case of a square root sign, which is always going to be a multiply, a number touching any grouping symbol, like a parenthesis, a bracket, a curly brace, an absolute value bar, or a radical symbol. Side by side means multiply. So when we take stuff from underneath and we simplify it out to where the 5 is, it's going to join the 5 times that's already out there. All right, let's break down. We're only breaking down the 200, n to the first, n to the second, r to the fifth. That's underneath. All right, for 200, there's a bunch of different ways we could get started. 50 and 4, 102, 25 and 8, right? 10 and 20, right? It doesn't matter how you get started. In the end, we'll end up with the same prime factors as long as we break down our tree correctly. So here for 10, 2 and 5. Over here, 5 and 4, which would get us to a 2 and 2. So again, I may have taken a different tree to get to those. I should have 3 2s and 2 5s. All right, 1 total m, 2 n's, and 5 total r's. 1, 2, 3, 4, 5 r branches. All right, let's put it all back together. The 5 times is on the outside, and everything else is underneath our square root sign. So 3 2s, 1, 2, 3, 2 5s, an M, 2 N's, and 1, 2, 3, 4, 5 R's. Again, right now, if I go 2 times 2 times 2 times 5 times 5, and I don't get 200, I'm going to stop and I'm going to go back up to my tree and see where I made a mistake. All right, from here, we're looking for pairs of items underneath, because one pair underneath is one number that can get simplified out because it's a perfect square. So this 2 times 2, that's a pair of 2's, represents the square root of 4. The square root of 4 is just a 2 that can get simplified out. So this one box represents 1 2 that got pulled out. So gone in here, 1 2 out here. All right, a leftover 2 that has to stay inside. A pair of 5s represents a 25. 5 times 5 is 25. So square root of 25 here would give us 1 5 that's going to get simplified out. All right, no pair of m, so m has to stay put. There's a pair of n's, which is n squared. So square root of n squared represents 1 n, not 2, that would get simplified out. All right, we got a pair of r's and a pair of r's. We have 2 pairs of r's. So this pair of r's, r squared. Square root of r squared here would give us 1 r out. This square root of r squared would give us a second r that came out. And then there's 1 r that doesn't have a pair that has to stay put underneath. All right, so let's go to our leftovers. We have a 2 times m times r. All right, let's do our math out here. 5 times 2 is 10. 10 times 5 is 50. Times n times r to the second. Square roots of 2 m r. Good final. Boxer on in. Most simplified version. 50 n r squared, square roots of 2 mr. Our goal for the second part of learning today is, what if we have a fraction that's underneath our radical sign? And how do we go about simplifying? It's a little bit tricky. So if I have something that looks like this, the square root of, and then the fraction of 68z to the second times y on top, all over 16z to the fourth. The first thing I want to do is I can break that apart into 2 separate little independent square root problems. So the first thing I'm going to show on my paper where it says break it up is I'm going to have one fraction where I have a square root on top and a square root on the bottom. And now I can write these as their own individual square root problems. It's the same problem. Having one big square root or 2 square roots on top of each other are equivalent, right? So 68z squared y and 16z to the fourth. So here's what you need to do. You need to take those 2 and do your simplifying process for each of them individually, which is a little bit time consuming, right? I'm going to do my numerator work separate from my denominator work. Once I get my prime factors, you don't want to multiply it all back out. You want to leave it as prime factors, simplified prime factors. You want to take those and stack them back up on top of each other. And then the way you simplify a fraction is whatever factors match on the top and the bottom, cancel or eliminate or simplify. So we want to start with our 68z squared y. All right, break it down. Again, there's a couple different combinations we could do here. I'm going to start with 2 and 34. Seems like an easy one. All right, 34, if we divide that again by 2, we'd get a 2 and 17. All right, 2 z's and a y. And here's where you want to be a little bit different, because we're not going to completely simplify yet. All right, so we want 2 times 2 times 17 times z times y. We want to get it to its prime factors, simplified prime factors. All right, so we have a 2 that's going to get simplified out. We have a z that's going to get simplified out. And I'm going to leave it like this as one big multiplier. And then our square root is one factor. The whole square root represents one factor. In this case, 17y, right? That's one big factor. So we have a factor of 2, a factor of z, and then this entire thing, which is the factor of the square root of 17y. When we go to stack them back up on top of each other, if the bottom has a 2, a z, or a square root of 17y, they will eliminate or cancel or simplify. All right, so let's go over here. Square root of 16zw. Now, there's 2 ways to do this problem. When I look at this and I say, wait, 16 is a perfect square, I could just go to, well, it's a perfect square. I know the number. Or I could still do my tree and I'll end up with the same result. So let's do our tree. I'll show you how I could have sort of shortcutted this one because it is a perfect square. All right, so I would say, all right, I got a 4 and a 4, a 2 and a 2, and then 4 z's. Z, 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 Z. And then I would have put it all back underneath. 2 times 2 times 2 times 2 times Z times Z times Z times Z. And then I would say, all right, I got a pair of 2's, so a 2 gets pulled out. Times, I got another pair of 2's, a 2 got pulled out. I got a pair of Z's, so a Z gets pulled out. And I have another pair of Z's, so another Z got pulled out. And there's nothing left over, which tells me the original thing was a perfect square. All right, so that would be the work way of getting to the fact that it was a perfect square. Or I could say Z to the 4th would give me 2 Z's, because I have 2 pairs. And 16 would give me to this 2 times 2, or 4. All right, I want to leave it like this, though, as my prime factors. So if you go straight up here to, I have 4Z squared, right? If I just know that because it's a perfect square, you still want to get to your prime factors and write this out as 2 times 2 times Z times Z. All right, so just be careful. You want just your prime factors left, and your square root part is one big factor. So you have to do all the multiply underneath there. That's one big factor. All right, so now we're going to take this guy, right? This is our numerator. It goes back on top. And we're going to take this guy, and it goes on the bottom, right? So we're going to have a fraction. We're putting it back together now. And we're going to have 2 times Z times square root of 17y. That's our top there. That's what we got when we simplified our numerator. Over a 2 times Z, which was our 4Z squared from the bottom. Now, here's the rule for simplifying fractions. If a factor is identical on top and bottom, they eliminate or they cancel each other, and they simplify out. All right, so if I have a 2 on the top and a 2 on the bottom, we'd say those cancel off. All right, if we have a factor of Z up here and we have a factor somewhere of Z down here, those would cancel off. Now, our only other factor up here is the entire square root of 17y. To be able to cancel that, down here would have to be that entire thing, the square root sign, a 17 with a y. Not just a 17, not just a y, but the whole thing together of square root of 17y, so be careful. So there's none of that down here. There's no other 2's and Z's up top. So now we know our simplified version. Put it all together. Final answer. On top, we have the square root of 17y. And on the bottom, we have 2Z. That would represent our most simplified version. All right, let's try another. These are a little bit tricky. All right, we want to simplify here the square root of 32 times a to the 5th times b squared. So my first step is I'm going to make that one individual square root on the top. 32 a to the 5th b squared. Before I even go to my 2 work blocks. And then all over our square root of 9a squared b to the 6. All right, now we're going to take this guy over here. We're going to take this guy over here. And we're going to do our simplifying process for each problem. All right, let's start with our 32 a to the 5th b squared. I don't know, 8 and 4 is a way to get started. 16 and 2 would be a way to get started. 4 is a 2 and 2. 8 is a 2 and a 4, so another 2 and 2. And then 5 of these. A, and 2 of these. Boom, 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 boom. All right, put them all back together, simplify whatever we can. So we have 5 total 2's. 5 A's, 2 B's, 2 B on not 2 B. All right, we're looking for pairs of perfect squares. So square root of 4 here is a 2. Square root of 4 here is another 2. Square root of a squared here would be an A. Square root of a squared here would be another A. Square root of b squared here would be another B. And then we still have the leftover. Remember that whatever's left over here is one factor to put it all together. All right, 2a. All right, so 2a with a square root sign is one big factor. I'm going to leave it just like that so I can see all of my prime factors when I stack it back up to do that eliminating. All right, don't make this 4a squared b because then it gets hard to see what can cancel out. All right, over here we have a perfect square again. 9 is a perfect square of 3. A squared is a perfect square of a. And then b to the 6 would create 3 groups of b's, right? B times b is b squared. B times b again would be now our b to the 4th. And then another b times b would be our b to the 6th. So we have 3. 1, 2, 3. If I just blew your mind by doing that in my head, do your treat. You'll see that everything was part of a pair and everything went out, which means there's no square root left over. If everything gets boxed, right, if everything in here is boxed, you just happen to have a perfect square in the beginning, which is fun if you took this more like long scenic route to get there. All right, let's stack them back up. This is the top. This is the bottom of our fraction. Let's start eliminating. All right, so 2 times 2 times a times b times the square root of 2a. Remember, to eliminate this square root of 2a, it would have to match. It would have to be the square root with 2a underneath it on the bottom. So be careful. All right, so 2's up here, no 2's down here. There's some a's on the top and the bottom. There's a b on the top and the bottom. And nothing else matches. So now we have to multiply it all out and get one big final simplified thing. So 2 times 2 is 4 times a. So 4a still times this square root of 2a. So square root of 2a is our simplified top. All right, 2 and 2, a and 2a. All right, 3 times b would give us 3b squared on the bottom. All right, best possible, most simplified version. 4a square roots of 2a all over 3b to the second. All right, last one, because I know these ones are a little bit trickier. All right, we're going to break it up. 2 separate problems. Square root 720, n to the 5th, n to the 7th, all over square root 45, n to the 7th, n to the 3rd. All right, this guy goes here, this guy goes here. Let's do some math. Let's simplify them separately. All right, let's start with our 720, m to the 5th, n to the 7th. When it ends in 0, if you cover the 0, right, that represents a 10. You cover it is the other number over here, 72. So that's one way to get started. All right, from here, 10 is 2 and 5. You know that one. You might have to do a little bit of guess and check over here with the 72. I don't know, one combination that works would be 18 and 4, 9 and 2, 6 and 3 over here, something like that. So 3 and 3, a 2, and then over here a 2 and a 2. All right, 1, 2, 3, 4, 5 emmers. Oh my, 1, 2, 3, 4, 5, 6, 7. All right, let's put it all back together. Got a lot going on here, so be careful. All right, start with our smallest. We have 4 total 2's. 1, 2, 3, 4. 1, 2, 3, 4. I'm going to eliminate here just to make sure I get everything. All right, after that, we have 2 3's. They're right here. And then a 5. All right, 5 m's. Ah, 7 n's. I'll end up over here. All right, let's start looking for pairs called perfect squares. All right, square root of 4 right here is a 2. Another square root of 4 here is another 2. A square root here of 9 is a 3. Gone. 5 stays put. All right, square root of m squared is an m. Square root of m squared again here is another m. Square root of n squared is an n. Square root of n squared again is another n. Square root of n squared again is another n. And then we have leftover 5 times m times n. So square root of 5mn. All right, those are our prime factors. I'm going to leave it just like that. We have a 2, a 2, a 3, an m, an m, an n, an n, an n, and a square root of 5mn. For this to cancel, it would have to match the whole thing. The square roots on the 5, the m, and the n all underneath. All right, let's go here. 45 is not a perfect square. All right, so we have to do our tree here. All right, 9 and 5. 3 and 3. Done, done. 7 of these. 1, 2, 3, 4, 5, 6, 7, and 3 of these guys. 1, 2, 3. All right, let's put it all back together. All right, we have 3, a 3, and a 5. That's this. Boom, boom, boom. 7 m's. 1, 2, 3, 4, 5, 6, 7. Gone, gone, gone. 3 of these. All right, let's start looking for our pairs. All right, we got a 3. Pull it out. Square root of 9 here. 5's left over. We have an m here. We have another m. We have a third m. one m left over, leave it alone, and then an n that can come out, and then all our leftovers is one big factor of 5mn. All right, so we have 3mmn and a square root of 5mn. If any of those match, what's over here, they'll simplify. This is on top, this is on the bottom. Put it back into your fraction. All right, so we have 2 times 2 times 3 times m times m times n times n times n times the square root of 5mn. All over 3 times m times m times m times n times the square root of 5mn. All right, now you should be looking at these and saying, I see that these now completely match perfectly, and that's when it would cancel, right? The square root portion is its own factor, and it can only cancel if it matches perfectly to the bottom square root portion, so be careful. All right, now there's 2's on the top and on the bottom, so those are both going to stay. A 3 that matches, an m that matches, another m that matches, and then an n that matches. And then we're going to multiply whatever is remaining to get our best possible, most simplified version. All right, on the top, we have 4n squared. All right, 2 times 2 is the 4, n times n is the n squared part, no more square root. On the bottom, all that we have left is an m. Whew. All that 4n squared over the value of n. All right, happy square rooting. See you guys later.